Hey there, kiddos. Today we're doing linear equation applications, and you should know by now, since you've taken math, when you see applications, that means word problems. So this will be a fun little video for you. Hope it can help you understand how to use some lines to model real-world problems. So that's our essential question today. How can I understand and use linear equations in real-life applications? And again, when you're thinking linear equations, think lines. That's what we've been doing. Let's deal with our first problem. Our first problem is about buying an apartment, and so I figured I would throw up this nice little picture of this attractive young couple's first apartment. This was a mini apartment that we rented in the very first year of our marriage. It was my second year of teaching, and this room was about 1/4 of the apartment. See how big it is? Very, very tiny. Over here was our very tiny bedroom. This wall didn't even come up the whole way, so it was actually kind of all one big room, but we loved it. It was super mini. Our apartment in Morocco is way better. Anyway, let's look at the exact example. You are moving into a new apartment, much like Mr. and Mrs. G were when they were first happily and youngly married. There is a one-time cost of $2,000 to buy the furniture from the previous owner. Also, rent is $600 per month. All right, so we got an upfront cost to buy the furniture. We got a cost of $600 per month to rent. So let's write a function to calculate your total expenses as a function of time. That's kind of a confusing sentence, but basically what it's saying is when you see something that says as a function of time, that means time is going to be the input, or think x. This is the thing we're plugging in. I'm not going to use x here, I'll use t, but it's the part of the equation that I'm plugging into. Total expenses is going to be the output. Think y. Again, we're not going to use y here, but think the thing you get out, it's the y. Here's how we'll write it. So e of t, that's function notation. It says expenses is what we're getting out when we plug in a certain value for time. What does that equal? Well, let's think about our expenses here. I have a one-time cost of $2,000, and then I have $600 per month. So thinking about t as time, shouldn't I do 600 times t? Because as the months add up, as I get into month 2 and 3 and 4, I'm paying $600 each month. Repeated addition is multiplication. So 600t tells me how much rent I've paid. But then I also have this one-time cost of $2,000. I only pay that once, so I shouldn't multiply it times t. It's just added on, even when t is 0, even before I've even paid a month of rent, I have paid the $2,000. Cool. Next, let's sketch a graph for this function, and this is going to be a very sketchy graph. T, remember how we said it's kind of like the x, it's the input, so we're going to put it along this axis, and t is counting up in terms of months, so we should label that with just nice integer values. However, our y-axis, which in this case is our e of t axis, our expenses axis, that's going to be in terms of money, right? Even at month 0, I'm already starting way up at $2,000. So let's just start the graph. Let's do it in terms of 1,000s. I should probably say dollars there. So 1,000, 2,000, 3,000, 4,000, 5,000, and so on. So in the first month, or actually in the 0th month, when t equals 0, that term goes away, and I'm left with just 2,000. So when t equals 0, I'm at 2,000. Or think about it this way. Isn't this in slope-intercept form? Here's my b. Remember, b is the y-intercept, so I'm starting at 2,000. Then from there, I'm adding on 600 per month. So in the first month, I'm 2,000 plus 600. So right about there. In the second month, 600 times 2 is 1,200, plus the 2,000 is 3,200. So now I'm right about here. Or think about it this way. This 600, isn't that the slope? So from 2,000, I'm going up 600 over 1, up 600 over 1. And I know our scale is weird, but I really am going up $600 over 1 month. So that's my slope, and it looks like, oh, I lost my axis. It looks like my line really should be doing something like this. Let's identify the parts of this function. We already talked about the fact that 600 is my slope because you know slope-intercept form, and 2,000 is my y-intercept. But let's think about what that means in context, because what it means in this context is going to apply to other contexts as well. First of all, let's talk about the 2,000 because we talked about that first. Wasn't this kind of the initial cost, right? That was the cost before I even started paying rent. So the y-intercept in real life problems has to do with kind of the initial value, or in this case, the initial cost. And that's what it's going to be every time. That y-intercept is the initial value. The slope is like the rate of change. This is how much my costs are changing each month. Every month I have to pay 600 more, so that's my rate of change, 600 more each time. Let's talk about what a reasonable domain is. So if you remember, the domain is all of the x's that you can plug in, or in this case, all of the t's that I can plug in. Can I go lower than 0? Definitely not. Can I go higher than, say, my graph? Can I go higher than 6? Yeah, definitely. So doesn't t start at 0 and then kind of go up from there, right? So these are all the different t values that I can plug in. I start at 0 and then I'm going up per month. Technically, for this problem, I probably shouldn't have drawn the line, because isn't it true that you only pay rent once per month? So probably my function should be just a bunch of dots on the graph, since I recognize I'm only paying once per month, and that's reflected in my domain. I'm only doing integer months. I'm not, for example, doing 0.5 or like 1.25. I never pay then. I only pay on the month. So there's my domain, the numbers I'm plugging in. Next, I need to ask about the range. Range are the values I can get out. So that's my E of t. The lowest value that I can pay is 2,000, right? If I have not owned the apartment at all, I've just bought the furniture, it's at 2,000. Then after the first month, I've now paid a month of rent, so I'm at 2,600. Then I pay in the second month another rent, another 600, and so on up from there. So there's my range. The lowest is 2,000, and then I'm going up in increments of 600. Finally, how much will you have spent after 5 months? Since I already have the function, this is a really easy thing to calculate, and let me show you how the notation would work. I'm going to say E of 5, because 5 months equals 600, and I'm plugging in this 5 everywhere I see a t, obviously, because 5 is my t. So in my equation, I had 600 times t plus 2,000, but instead of t, I'm going to have the 5. And let's just calculate that. 600 times 5 is 3,000, and then adding 3,000 to 2,000 is 5,000, and let's use proper units, it's $5,000. Okay, let's look at just one more example, and I will try to make it quick for you. Here's example 2. Tickets for a school show cost 50 dirham per adult and 25 dirham per child. The total ticket sales are 1,000 dirham. So, I want to write an equation to model the situation if the number of adult tickets are represented by A and the number of child tickets are C. You have seen equations like this a lot before. They are not going to look like this sort of equation. Let's just think about this intuitively. If I have $50 per adult ticket, wouldn't the total cost from the adult tickets be represented by 50A? And then likewise, I'm going to be adding to that 25C because I have $25 per children's ticket sold. And I'm told that the total ticket sales are 1,000 dirham. So this equals 1,000. And again, it doesn't look like our slope-intercept form of an equation, but what does it look like? It does look like standard form. So in order to sketch a graph for this function, it would be a really good thing to use intercept method. And remember, for intercept method, I'm plugging in 0 for A, and then I'm going to plug in 0 for C. So plugging in 0 for A, I have 0, we know that this term goes away, and to solve for C, I'm just dividing by 25. 1,000 divided by 25 is 40. Okay, and now to find the other intercept, let's plug in 0 for C. When I plug in 0 for C, that term goes away. I divide by 50 to solve for A, and it looks like A is going to equal 20. So A is 20 when C is 0. And let's just sketch a real quick graph of this. I'll make my A axis the X, I'll make my C axis the Y, and just over 0 up 40 is, yeah, it's going to be right here. And then over 20, let's say 40 is over here, over 20 up 0 is going to be right about there. So our line goes down like this. What does the A-intercept mean? Here's the A-intercept, right? It was this point. What did that mean? Let's think about it in context. That 20 is A, and the C is 0. So think about it. That means 20 adult tickets and 0 children's tickets. In other words, the A-intercept is telling me, like, kind of what's the maximum adult tickets that I could possibly sell. The maximum adult tickets are when the children's tickets are 0. So the A-intercept here actually means when are the adult tickets at their max, and you can kind of see that in the function. Isn't this the highest we ever get for adult tickets? Here, here, here. This is all lower values of adult tickets. Way down here it'd only be 5, but over here on the intercept I'm selling the maximum of 20. Finally, we want to list 3 possible ways the tickets can be sold. Well, hey, I already have 2 of them, right? I could have, let's make a little table, adults and children. I could have 0 adult tickets, then 40 children's tickets would be sold. I could have 20 adult tickets, and then 0 children's tickets would be sold. Let's use a sort of intercept method of finding some other value of tickets. For example, let's say that I sell, let's do 20 children's tickets. If I do 20 children's tickets, 25 times 20, let's see, isn't that going to be 500? So 50A plus 500 equals 1,000. If I subtract that 500 to the other side, that's my situation. And then dividing through by 50 gives me that A equals 10. So if my children's tickets are at 20, I just found out that the adult tickets are at 10, and that should make sense on the graph. Let's look. Let me just sketch in some more values here. If I have 20 right here, if I'm going over 10 and up 20, doesn't that look like a point on the graph? It does. So that graph contains all the possible points that I could possibly have. We know that I could probably only be using integers here, and in fact it'd only be certain integer values, but the graph in general should contain the different points I can use in this problem. Summary. Now, just real quick, I flew through those word problems. If you had issues with any of them, please pause, rewind your video, just think through them a bit more to see what I was doing. I'm going at a maximum possible pace to keep the video short, but word problems, it's just a little bit longer. So let's talk summary. When modeling a function with a linear equation, this is like example 1. The slope is going to equal the rate of change. The y-intercept is going to be kind of the starting value. That's the main takeaway I want you to have from this lesson. Thank you very much for watching.